Now, we have already learned what a permutation is, but just to review, a permutation is when you have a certain number of objects and you want to arrange them in a specific order. And this is going to come up more important later in the unit when we learn combinations, because in a permutation the order is important, in a combination the order is not important. So if we had the letters A, B, C and we wanted to write all the permutations, well, we could think of a systematic way, all the ones that start with A, then all the ones that start with B, then all the ones that start with C. Of course, we have our fundamental counting principle already. A permutation is like a spaces question. You have 3 decisions to make. What letter is going to be first? How many choices? 3, then 2, then 1. And so when you're doing a permutation of all the objects in a group, that's where the factorial notation comes in nice, because you just have 3 factorial. There's our formula for the number of permutations taken r at a time. So if we were looking at some special cases, if you had npn, which is all the objects arranged in a row, like we did with ABC, then the formula just simplifies to just be n factorial. And when we use the formula, though, in this case, we do get a 0 factorial. And we remember from before that we defined 0 factorial as 1. And this is the reason why 0 factorial has to be 1, because sometimes it shows up in formulas, and we know the answer is supposed to be n factorial. So the only way that works is if in our formula we allow 0 factorial to equal 1. So here's an example. We can do this with the fundamental counting principle. We want a program where the order matters, 10 pieces, because you've got like some songs that, would be funny if they happened to be in the middle of the concert. Like right in the middle of the concert, you play O Canada, and everybody has to stand, and they're like, this is weird. So we've got 10 pieces. We want to make a program with 4 pieces, so we have 4 decisions to make. How many choices do we have for our first song? Any of the 10. Then there's 9 songs left, then 8, then 7. Of course, this is also equal to 10p4. So for the most part, we will do it with the spaces and the decisions, but sometimes on multiple choice questions, they have the answer written with the permutation formula. Of course, what does that 10p4 according to the formula mean? It means 10 factorial over 10 minus 4 factorial, which is 10 factorial over 6 factorial. And if you expand the bigger one, do you see that you would end up getting 10 times 9 times 8 times 7, because the 6 factorials would cancel out. Number of permutations of the word math. Now, if you're using all the objects, which we're using all the letters in math, you can just directly write that as 4 factorial. If you want to do the spaces, there'd be 4 spaces, 4, 3, 2, 1. But you might find out with words, especially since we have done those words with identical objects already, where you just count the letters. So you might get used to, oh, math, 4 letters, no repeated letters. It's just going to be 4 factorial. I think these are the hardest spaces questions. 5 people come in for math help, and there's 12 desks. The reason it's hard is all along we've been putting numbers into spaces, and that made sense. Students come into a class and there's desks, and what do you want to do? You want to put students into desks. It's hard to imagine putting desks into students, but that's kind of what has to happen here, because how many decisions do we have to make? We don't have to make 12 decisions. We only have to make 5 decisions. But this one, for whatever reason, is very tempting to make 12 spaces because you want to put students into desks. But instead, we have to say our spaces stand for decisions. How many decisions do we have to make? Not how many students do we put in desks or desks into students or something like that. 5 decisions to make. That first student comes in. How many choices do they have? 12. Now, if you're in here for math help and you're the first student sitting in one of those 12 desks, and that second student comes in and they decide to sit on your lap, that's a little awkward, right? So number of choices for the next student would be 11. They can't choose that same desk again. It'd be really awkward if that third person came in and sat on the other person's lap who's already sitting on somebody's lap. There's a game like that? It's not called math help. Okay. So we get 12, 11, 10, 9, 8. And of course, this is 12p5. So again, in that permutations formula, we start to see the connection that this number is always the number of spaces or the number of decisions we need to make. Now, if we count how many people are in class right now, 1, 2, 3, 4, 5, 6, 7, 8, 8, 12, 18 people, and there's 30 desks. How many seating plans could we make? So we would have 18 decisions to make because each of you would have to pick a spot. There's 30 spots to choose from. And this is where the formula is nice as compared to writing out the spaces, because there would be 18 spaces. And then you'd have to do 30, 29, 28. There'd be a lot of writing. So now with bigger numbers, the formula works out quite nicely. And if I said, I'm going to do it random, and you have to figure out where everyone's going to be seated for this afternoon's test, and if anybody can guess it right, they not only get 100% on the test this afternoon, I'll give them 100% in this course and give them a free calculus credit. Like, wow. Okay. What are our chances of winning? 1 in, well, let's figure out how big that number is. Is it big? Is it small? You know where to find the NPR button on your calculator? One in, now, at first it doesn't seem so bad. 1 in 5.5, that would mean in a class of 20, 4 of you are going to get 100% in a bonus calculus until you look at the end of the number where it has an e to the 23. Oh my goodness. So what does that mean? That's basically rounded 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23. That's approximately what that number is, give or take a couple quadrillion. What are your chances of getting the free calculus credit and 100% in the course? Not great. Right? You'll take the odds? The NPR button is right above the factorial button. So if you hit your math button and go over to probability, it'll be there. And you have to type this number in first, then go to your NPR button, and then you'll type in this number after. Yes? I do. All right. We are going to change the title of this to match the same thing we did earlier. Earlier, we called these identical objects. So we're going to change this title to say permutations with identical objects. So how would you do egg? Three factorial over 2 factorial. Because it normally has 3 letters. But since we have the identical objects, the 2 G's are the same, we have to divide by 2 factorial. In B, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So normally this would be 9 factorial. What do we have to divide by? 3 factorial for the S's. 2 factorial for the I's. And 2 factorial for the P's. If you wanted to divide by 1 factorials for the A's and E's, you could, but that makes no difference, so we usually don't write it. Now, these egg, Assissippi, Mississippi kind of questions come up in more than one way, but what you're looking for is, are there identical objects in the thing that I want to count? Because if there are identical objects, then I can use this strategy. So here's our next question. Contractor sold model homes of 3 different types, 3 of model A, 4 of model B, and 2 of model C. Then they make a new development and I'm going to put these houses on a street. How many ways could they be arranged? Well, once we recognize that we have some identical objects, then one of the strategies that we use is to write it out as a word with those identical objects. So in this case, 3 of model A, I can represent that with 3 A's. And then 4 of model B with 4 B's, and finally 2 of model C with 2 C's. There's 9 letters there. Normally that would be 9 factorial, but because we have identical objects, we divide those out. And we've already looked at this type of question as well. So John lives 3 blocks north and 6 blocks east. Tell me, which corner does John live in? Top left, bottom right. He's got more than one house? Wouldn't it be bottom left? He lives 3 blocks north, so his house has to be north, and 6 blocks east. Oh, look at that, you guys. Yeah. You would have got it if I would have given you 5 guesses. All right. And then his school is right here. So to get home, he needs to, assuming he stays on the road and always walks closer to home, needs to go north 3 times and east 6 times. That's how you say that word. That would be, I'm sure when John gets home, his mom asks him, "Oh, how did you come home today?" And he probably just responds, "Me." So if we think of this as an identical objects question, this would be 9 factorial over 6 factorial, 3 factorial. Do you remember our other technique for figuring this out, where we count the pathways along the way, where all of these will be 1s? What will this, how many ways can you get to this dot right here? 2 ways. And this will be 3, 4, 3, 4, 5, 6, 7. How did we find this one? Add those 2 up. 6, 10, 10, 20, 15, 21, 28, 35, 56, 84. And those are very pretty numbers, but you don't know why they're pretty yet. So, but I'll teach you maybe in a week or so, next week, why those are pretty numbers. Not just because I have nice penmanship. Okay. We're going to look at one last topic before we work on this stuff. This is a new topic, permutations with a restriction, and that restriction is things want to be grouped together. Because sometimes you want to make arrangements of things. Maybe you have a collection of DVDs at home, and you want to group all of your action movies together and all of your drama movies together, and then all of your cartoons together. So you own 3 action movies, 5 dramas, and 185 cartoons. So the number of ways that you arrange things is first you arrange your groups. So in our example that we just made up, we had 3 groups, action, drama, and kids movies. So you would start off with 3 factorial because you decide, well, do I want my cartoons first, or do I want my cartoons in the middle? How do I want to put those groups on the shelf? Then once you've decided which group is going to go first, say you decide my action movies are going first. I have 3 of them. How many ways can I rearrange my action movies? Well, since there's 3, 3, 2, 1, be 3 factorial. And then you put your 152 cartoons. Well, that can be done. There's 152 decisions to make then, 152 factorial. And finally, your 5 drama movies, 5 factorial. But let's talk about a collection that's probably more likely. My math books. So I've got 4 calculus books. We're going to assume all the books are different. 5 algebra books and 4 geometry books. And I want to put them on one shelf, but I want to keep the calculus books together. I want to keep my geometry books together and my algebra books together. So my first decision is how am I going to arrange those groups? So when we're showing our work, we write 3 factorial, and underneath it we just do a quick description to describe that's my number of groups. Then once I've arranged my groups, how many ways can I arrange each of those groups individually? Again, just a brief description underneath saying what that was that I was organizing. 4 geometry books. And you multiply those all together because basically this is a fundamental counting principle within a fundamental counting principle. We have decisions to make, and each of those decisions have decisions within decisions. So decision 1, how am I going to arrange my groups? And then I have 3 decisions in there. Which one first, which one second, which one third. Decision 2, how am I going to arrange my calculus books? And then that's 4 factorial in there. Decision 3, decision 4. So this is like the fundamental counting principle, but our number of choices in each decision are some really big numbers. So we got 5 friends. They come to a park bench and they want to sit down on that park bench, and Jill and Bill want to sit together. So this becomes a grouping question because we've got Jill and Bill grouped together. Now, there's sort of 2 ways that people look at this. Either they think of Jill and Bill as one person because they're always together. And then they think of this as only how many ways could I arrange 4 people on a park bench? That would just be 4 factorial. Or we can think of the 4 factorial at the beginning as our number of groups because we have Jill and Bill as one group, and then each of these other people, Amy, Lee, and Tom, are individual groups of 1. So we have 4 groups. The grouping strategy says after you've arranged your groups, you then go into your individual groups and see how many ways you could arrange them. Now, Jill and Bill could be Jill and Bill or Bill and Jill. So when they sit on the park bench, it depends if they want to hold left hand, right hand, or right hand, left hand, right? So we've got 2 factorial ways for that. We wouldn't have to write 1 factorial for the other 3 groups because there's only 1 in there, but it's not wrong if you do. If you want to get into the grouping strategy where you number of groups factorial, and then each group you look at how many ways they can be arranged, you could put that down. This is going to be 48 ways. that Jill and Bill can sit together. Part 2. Things seem to be spreading. Poor Tom. Now Jill and Bill want to sit together, and Lee and Amy want to sit together. Don't worry, Tom gets his revenge in part C. Okay? So now, when we're thinking of how many groups, we've got Jill and Bill together, we've got Lee and Amy together, and Tom all by himself. So our number of groups is 3 factorial. Then when we look in each of those groups, Jill and Bill, left hand, right hand, left hand. Lee and Amy, left hand, right hand, right hand, left hand. So this would be 2 factorial for Lee and Amy. And you don't have to put the 1 factorial for Tom, but if you're feeling really bad for him and you want to include him more in the question, you can do that. Okay. Part C. Now in part C, we're just wanting to make sure that Jill and Bill don't sit together. I don't know why these 5 friends still come back to the park bench, but they do. But now Jill and Bill must not sit together. We're not worried about Lee and Amy. They're sort of on again, off again. They can sit together or not. In this question, we're just concerned that Jill and Bill don't sit together. And I mentioned this earlier. This is where the not strategy really comes in. Because if we tried to count this directly, it gets complicated. Because, oh, if Jill's sitting in the first, then Bill can't sit in the second. But Jill could sit in the second, then he can't sit in the first and third. Whew. So it's easier to count all of the permutations. How many ways could you arrange 5 people on a bench? 5 factorial, 120, easy to count. In A, we already counted the bad ones where Jill and Bill were sitting together. It was good back then in part A, but now it's bad in part C. Okay? And if we take all the ways and subtract the bad ways, what we're left with is 72 ways where Jill and Bill are not sitting together. We're going to leave permutations with cases for tomorrow.